So I think we can get started. Good morning, good afternoon, and good evening, everyone. Welcome to the seminar today, co-hosted by the San Diego State University Computational Science Research Center, CSRC, and the San Diego State University Department of Aerospace Engineering. My name is Xiaofeng Liu. I'm an associate professor at the Department of Aerospace Engineering. The seminar today is the very first seminar in this new academic year for both CSRC and the AE department. To start the seminar, I'd like to ask Professor Jose Castillo, the director of the San Diego State University Computational Science Research Center, to give opening remarks. So Professor Castillo, please allow me to turn the podium to you.
Well, thank you, Xiaofeng. I just want to say that it's a pleasure to start the seminar season, I guess colloquium season, with a joint seminar with aerospace engineering, and particularly the topic of COVID. So this is an excellent choice, and looking forward to hear the seminar, and I welcome everybody, and thank you.
Thank you, Professor Castillo, for the opening remarks. So let me now introduce our speaker, Professor Christian Kähler. Professor Christian Kähler is a world-renowned fluid mechanics experimentalist, spearheading the effort in characterization of the aerosol transport behavior related to SARS-CoV-2 airborne transmission mechanism. He received his physics diploma degree from the Technical University Clausthal in 1997, and his PhD in physics from the George August University of Göttingen in 2004, and his habilitation from the Technical University in Brunswick in 2008. So from 1996 to 2001, Dr. Kähler worked at the German Aerospace Center, DLR, in Göttingen. During his tenure at Göttingen, he visited the University of Illinois at Urbana-Champaign, Professor Ron Adrian's research group in 1996 as a visiting scholar, and also visited Caltech in 1998. From 2001 to 2008, he was the head of the research group on flow control and measuring techniques at the Technical University Brunswick. In 2008, he became a professor for fluid dynamics and was appointed the director of the Institute of Fluid Mechanics and Aerodynamics of the university at the Dome of Bundeswehr, Munich. Professor Kähler's research covers a broad range of topics including the development of optical measurement techniques on the micro and macro scale in order to further investigate complex flow phenomena in macrofluidics and turbulent flows at subsonic, transonic, and supersonic conditions. Professor Kähler has co-authored over 100 archival publications and 200 conference papers. Furthermore, he co-authored the third edition of the Springer book on particle image velocimetry, which has been cited over 8,000 times. In addition to his dedication to his own research work, Professor Kähler also provides his leadership role in the world's fluids community in the capacity of top journal editors or editorial board members, conference or symposium organizers, and keynote and invited lecture speakers for numerous occasions across the globe, including his lecture that he delivered here at CSRC 2 years ago on SDSU campus. Since the outbreak of the COVID-19 pandemic, Professor Kähler has been serving as the first responder to the pandemic, representing the world fluids community by spearheading the effort in characterization of the aerosol transport behavior related to SARS-CoV-2 airborne transmission mechanism. In recent months, Professor Kähler's research on SARS-CoV-2 infection has generated a great deal of media attention, and Professor Kähler has become a much sought after advisor to policymakers. So today's seminar is a great opportunity for us to learn the cutting-edge research about the aerosol transport behavior related to the COVID-19 airborne transmission mechanism, which is within the realm of concerns for fluid mechanics. So we believe that today's talk by Professor Kähler will shed light on the appropriate physical measures to be taken to curtail the spread of the COVID-19 pandemic. So Professor Kähler, please allow me to turn the presentation to you. Thank you.
Yeah, thank you very much for the very kind introduction. I share now my screen. Let me see. Should be this one. So is it visible, my slides?
Yes, it's good.
Okay. So the work I'm going to present is, let's say, something I did together with my co-authors here, Rainer Hein, Thomas Fuchs, and Benedikt Mutsch. So they are working in my institute for quite some years, and they supported me in doing this quite fascinating research. And I hope I can show you a little bit of the achievement we could gain in the last 1.5 years since we started working in this field. So let me start with a little motivation before I come to the outline of my talk. So of course, prevention of SARS-CoV-2 infection, that is very important, and because of a number of reasons. The three main reasons from my point of view are because the virus will mutate and become more dangerous over time. That's one issue. And dangerous means it spreads with a higher velocity, or it becomes more deadly over time. So this is one aspect. The second issue is the vaccination we have will not protect us permanently. So we have to refresh that regularly. We don't know yet how often we have to do that. Maybe after 6 months, as for the elderly people in the moment in Germany, or maybe after a year or after 2 years, we don't know. But the problem is that the willingness to get the vaccination will decrease over the years. So maybe in the moment it will go up to 70%, 75% with some incentive, but consider what will be the case in 2 years, in 3 years, and so on. So that's the major problem or concern over the long run, and that's why we think that we need to use effective technology to save us before an infection, to keep the let's say the number of infected people on a low level. So that's one issue. And now, of course, the question is, how can you protect the people? And here something very interesting from my point of view has to be considered, namely the aerosol particle droplet problem. So what is the problem? The problem is that in physics or in engineering, we consider a particle or a liquid droplet as an aerosol particle when its diameter is in the range of 1 nanometer up to a few hundred micrometers. So that's something stays, or that's a particle that stays for quite some time in the air. It doesn't fly ballistically, and it doesn't sink rapidly in still air. So that's the technical or the physical definition of an aerosol particle. But in medicine, they consider particles smaller than 5 micrometer as an aerosol particle, and particles larger than 5 micrometer as droplets. And they teach in medicine that the droplet flies but ballistically and sinks quite quickly. This is, of course, wrong from the physical point of view. And to make a long story short, the problem with this is not only that we have a problem in communicating with each other. So there's a misunderstanding between the disciplines. But more important is that the safety measure you apply depend on what you think makes the transmission of the virus. So when you consider it's a droplet, then touching is a problem. And if you consider a droplet to be something which is dangerous, a poor mask will be good enough. But when an aerosol particle is a problem, then you need much better protection devices. And this is really a problem. And at the beginning of the pandemic, that people were fearing touching and stuff like this. But today, this is not a problem anymore. But since this controversy at the beginning, I thought it's better to make a transition back from or away from aerosol particles and droplets to another concept. And I will outline that in a second. But before, I like to outline this article here. So if you're really interested in the story behind this, and it's a very important story, make a screenshot here and have a look on this story to get deeper into it. So in order to not have the conflict with droplets and particles, which causes a misunderstanding between the disciplines, I introduced the concept of direct infection and indirect infection. So when we speak about a direct infection, it means when we are close together, then one person can, let's say, emit aerosol particles and tiny little droplets, and another person can, of course, then get infected. And of course, when this situation takes place, then it's clear you can protect from this direct infection route when you increase the distance, when you use a face mask, or when you have some protective screen in between. And the second one is the indirect infection. So the indirect infection means you have the aerosol particles with the virus in the room. The full room is occupied with them. And here you don't need to interact with a person. Here you can get infected because of the contamination of the room. Here, distance doesn't matter. A simple mask doesn't help you from an infection, and also protective screen will not help you. Here, you need to ventilate, or you need to use mobile air purifiers or something, HVAC systems or something like this. So if we use this concept here, direct infection, indirect infection, then we don't have to worry about droplets, aerosol particles, aerosol nucleus or something like this. So that's why I will use this concept in the following. So I will talk a bit about masks, protective walls, air purifiers, and some applications. That's basically the outline before I come to the summary. So the first question, of course, is when you are talking, singing, breathing, or something like this, how far are you distributing the aerosol particles in the room over a short time? And here you see an experiment where myself is, I'm sitting here on a chair talking, a light sheet is illuminating a plane, and you see here where the flow velocity is larger than the mean flow velocity far away from my head. And you can see when I'm simply talking, then the aerosol particles will stay in a region like this. So it's maybe 40 centimeters apart. So when you have a distance, let's say one meter away from each other, and you are talking, then you are pretty safe in these circumstances. So that's why we can say when we are displayed by, let's say, displaced by 1.5 meters, we are pretty safe in a conversation, for instance. And that's why distance is extremely important. So now, when we study what's happening when we are coughing, then you can see that here the aerosol particles, which are here more in green and red and so on, they are distributing far further away from the head. So we are reaching here something like 1.5 meters. As coughing is quite seldom, so you don't have to worry so much when you are 1.5 meters away and some person is coughing, because it will be a little event, so you will probably not get infected. But when there is, let's say, a repetition of the coughing, so then you should go to even larger distances to be safe. Anyhow, what you could do else is you could use a very simple mask. So this can be a surgical mask or a mouth and nose cover. And when you are now coughing, then you see you keep the aerosol particles very near to your head. So this makes, let's say, the direct infection risk very low, even when you are coughing, sneezing, talking, singing. All this is not a problem at all when you keep some distance and you're wearing this simple mask. And that's why these simple masks are already very important to minimize the direct infection risk. But when you are using this mask, the problem is that they have a leakage around the mask. And so all the aerosol particles are getting out sidewise, and also some here around the nose. So these masks are very, very helpful in face-to-face conversations, but not very helpful when you are sitting side by side, as in a classroom, for instance, as in a train or in a taxi, or in an office, for instance. So you always have to keep in mind they are very good for face-to-face conversations. There they can minimize the direct infection risk, but not when you are sitting side by side. Then they are more or less useless. They may also amplify the infection risk because of the transport of the aerosol particles sidewise to the neighbor. So that's one issue. But the other issue is when you are wearing this mask in an environment where you have all the aerosol particles with the viruses in the surrounding, then you will inhale all these viruses through the gaps at the, let's say, edge of the mask. So you cannot protect yourself from the indirect infection risk. And this is something which is very important. So you have some protection for others, in particular for face-to-face conversation, but you cannot protect yourself. And that's also outlined in the regulations of this mask when you are making the qualification of the mask. So that's very important to understand. That's why in hospitals, for instance, or if you're really want to not get infected, you should not wear this kind of mask. You should wear N95 in the US, for instance. So now what we did else is we wanted to figure out how well the filter material of the mask is, because at the beginning of the pandemic, the people thought it's good to use some clothes or some simple mouth and nose covers to protect yourself. And so we have here a little channel. We have mounted the filter material here. A laser light sheet is coming from the side to illuminate the flow area before and behind the filter material. And when we have a flow now here with aerosol particles, then we see the aerosol particles with the camera before the filter material. And if we see them behind the filter material, we know the filter material is not very good. If we don't see anything behind the filter material, then we know, of course, the filter material works very well. And here, this is, for instance, a very common surgical mask. And you see the aerosol particles are coming from the left-hand side. They pass through the filter material and you see them on the right-hand side. So the main protection of the surgical mask is not the filtering capacity. It doesn't have a real filtering capacity. It's to limit, let's say, or to have some flow resistance so that the spread in viewing direction is limited, what you saw before, but the filtering capacity is very low for this kind of mask. So now we have an N95 mask, the same experiment, and you see we have a lot of particles coming from the left-hand side, going through the filter material, and we see almost no particles on the right-hand side. And this is what you really need when you want to protect yourself. So you need a mask with very good filtering capacities, and on top, which seals very well here so that you don't have any gap flows. And if you have such a mask, then you can protect yourself from a direct infection, but also from an indirect infection. And you're not protecting also yourself, only yourself, you're also protecting others. Because when you are an infected person and you are exhaling all the aerosol particles, they will stay in your mask, so they are not distributed over the room. And that's of course why these masks are recommended, let's say, in this pandemic by many people. So that's basically what I have outlined here. So the simple masks are already pretty good in face-to-face conversations for the direct infection risk minimization, but of course they do not protect yourself. Then you have to use a better mask to protect yourself and others in a better way. And that's why these masks are recommended. But now the problem comes, because you cannot wear these good masks all the time. That's physically too stressful. And that's one major drawback of this mask. And now the question is, how can we protect ourselves in offices, in classrooms, restaurants, and so on, without using these kind of masks? Is it possible or is it not possible? So let's have a look at first on protective walls. We see these protective walls all around the world in many environments. And here I would like to show you a little video where we see a simple protective wall over here, transparent, let's say, Perplex wall. And this person is now, let's say, exhaling some aerosol particles, and you see what's happening. So consider you are sitting here. It looks good. You are more or less safe, but some particles can overcome the barrier, and you may get a little, let's say, contamination. Of course, the direct infection risk is reduced enormously already because you're not getting the direct particle stream into your lungs. The particles have to go around this barrier. And of course, this limits or reduces the virus load enormously. So you can stay longer together with a person like this. Anyhow, if you, people in fluid mechanics know, if you have, let's say, a barrier as seen before, and you put a little, let's say, edge, as shown over here, around this barrier, then you can enormously reduce the crossover here, because the particles form a vortex over here, and the particles stay on the left-hand side. They are not going on the other side. I play this again. And of course, all the people in fluid mechanics know this effect, but that's why we recommend, whenever you are using these kind of barriers here or protection shields, make this kind of, let's say, additional edge, and then you are much more safe against direct infection. We have installed this kind of Perplex walls here in many classrooms in Germany, and of course they, if you consider it here, they have a size like this. That the kids have a very good direct infection minimization when they are working on the table, but also when they are sitting relaxed in the chair, and also when they, you know, whipping back and forth around the chair. So they can always talk to the neighbors, they can cough, they can sing. They will not directly infect the neighboring person thanks to this protection screen. On the other hand, you don't see this kind of protection screen from this boy to this one, because here we have a large distance. So here the distance is responsible to make it safe, and for short distances it's the protection wall. So if you do it like this, you know, then the direct infection risk will be no problem anymore. And that's why this kind of protections here are also recommended by the Harvard Chen School of Public Health, by the CDC, and we have also recommended that already more than a year ago. And we have done many experiments also to demonstrate the capabilities of these walls. So what is important, of course, when you use this transparent protective walls with the surrounding edge, direct infection is not a problem anymore, even when you are sitting very close together. But over time, of course, the aerosol particles can occupy the whole room. And then you don't have a direct infection risk, but you have the indirect infection risk. And of course, this is problematic. And so we have to think about how we can eliminate the indirect infection risk as well. And of course, let's say here the air purifiers are coming into play. So normally you would say we have windows we could open, but I will show you later on that windows are not working well enough. You could say we have a very good HVAC system in the room. If you have that, use it. That's the perfect solution. But in many countries, you don't have them. So in Germany, for instance, or in Europe, we don't have them. So the question is, what can you do if you have a building without a high power HVAC system? And then mobile air purifiers come into play. And I would like to outline this in more detail now. So what is an air purifier? So basically, it's just a technical device with a fan inside, and the fan sucks the outer air through a little pre-filter, and then through, let's say, high quality HEPA filter of class H14, for instance. And then all the viruses and aerosol particles are staying here in the filter, and then the filtered air is getting out here on the top of the device. And then usually we have the free jet here going to the ceiling, and then going along the ceiling to the side walls of the room, going back or down, and then pushing all the dirty air back to the device. So that's how this works in principle. So these air purifiers are quite powerful. If you use professional ones, they are also recommended by CDC and WHO, for instance. And we have done many experiments in the past. And of course, the first question is, if you have a room, let's say 9 by 9 meter in size, which is a quite large classroom, and you place the air purifier at some location, let's say this location or this location, then the question is, how well will fixed aerosol particle concentration in the room be lowered as a function of the position in the room? So will it be lower here or compared to this location or this one, or will it stay contaminated here while it's getting clean over here? So that was the first question we have addressed in experiments. And first thing is, if you don't do anything, then the aerosol particle concentration over time stays on a quite high level. Actually, we have a little decay because no room is perfectly sealed, but it stays on a high level. And when we are producing aerosol particles here, then of course it can stay constant or even raise. So now when we switch on the air purifier, we see that the contamination drops down quite rapidly and then goes to a low level. So for instance, even after a couple of minutes, we have only half the aerosol particles in the room. And then let's say, yeah, we can see here after half an hour, there are less than 10% in the room. So we can keep a room quite safe over a long time. And the experiments show that because of the mixed ventilation in the room, it's not so much of an issue where you place the air purifier. Can be the corner, can be the center of the room, can be any other location. The decay will be always quite similar. And it also doesn't depend on the distance from the measurement location to the air purifier. So even when you have a, let's say, air purifier here, and you are considering the drop of the aerosol particles at this location, there's not much difference between the decay at this location and at this location. And that's because of the turbulent mixing you have in the room. We always have some turbulent mixing in the room, and that is the so-called mixed ventilation, and that ensures that you have always a very gradual, similar decay of the aerosol particles, no matter where you are in the room. But now there are three very important criteria you have to achieve when you are buying these devices to get rid of the indirect, or to minimize the indirect infection risk. So what are the three criteria? The first is the device must filter at least 6 times the room volume per hour. We can consider, when we have now the Delta variant of the virus, that we go maybe better to 8. That's recommended by some people. I still think something between 6 and 8 will be okay. So that's why I say at least 6. Second, you should use a filter of class H13 or H14 because they are especially built for this kind of task. So they are built for reducing or rejecting the virus. And that's why I recommend these kind of filters. And third, the devices shouldn't be so loud. So they should be less loud than 50 dBA, from my point of view. Because 50 dBA is usually a room or a classroom where nobody is talking. When we are talking, then we have 60 dB or 65 dBA, but 50 is a room where nobody is talking. And so that's why I think when you go to something like 45 dB, you will not hear the device. And you also have to consider that the noise of the device is very low frequency, very equal, so to say. So your brain will filter that noise out, that you don't hear it anymore after a few minutes. So it will not be a kind of noise you know from the street, from cars going back and forth. So this is very quiet and let's say not so much let's say no noise that really gets your attention. But when it's too loud, then you are switching off the device and then you don't have any protection anymore. And of course, the bigger professional devices, they produce not much noise. But the cheap, small devices, they can be quite loud. That's why I'm not recommending the simple one for professional applications in an office or in a classroom where you're staying or sharing the room with these devices for many hours a day. Okay, so that's what I can recommend when you're considering to buy these kind of devices. So let me show you some applications we did in the past. So we went into, let's say, a real school, and you can see here the computer room, for instance, and all the computers here are, let's say, placed at the wall, and of course the distance is quite small, so we have the protection walls in between the screens, and now you can see here the top view of the room, and we have here in this area the green dot, that's the air purifier, and the red dot, that's where the measurement location is. So the worst case scenario. So here is the measurement location in between 2 transparent side walls, and the air purifier sitting over here. So this is one computer room. Then this is the teacher's room, where we have, let's say, just the room where the teachers spend their spare time, also with all the protective walls. And we have set, let's say, a specific, let's say, air exchange rate. And surprisingly, the air exchange rate we set at the device was also very close to the one we measured by evaluating the exponential decay of the aerosol particle concentration. So you can be sure, even when you have a room with tables, with chairs, with computers, with protective walls, you are very close in regard of the rejection of the particles to the theoretical, let's say, solution. So this is very good, and we have that also in other rooms. So this is, for instance, the classroom under the roof. So here we have let's say a roof like this. So you would guess that in this environment it's not working that well, but it turns out it's similar to the, or it matches quite well the theoretical predictions. And here we have the kitchen, and here we have additional cleaning devices in the kitchen above the stove, and the door is opened from time to time. And also here we could measure, let's say, a high air exchange rate. And this experiments also showed that when you are using air purifiers to get rid of the indirect infection risk, you can always open windows or open doors or use this kind of HVAC system on top of that. It will enhance, of course, the rejection. It will be better for your health. So there is no negative interference between different concepts you can use for getting rid of indirect infections. So now I would like to come to some quantitative measurements in a laboratory. So we did also quantitative measurements here. You can have a look in our reports and so on. But I would like to outline this here in a bit more detail. Here we see again the aerosol particle concentration over time. And of course, when we have some contamination at the beginning and we are not doing anything, then you see the aerosol particle concentration stays on a quite high level, as we have seen before. So now what's happening when we open the window? So we can open the window and then we see, okay, it's better. We are removing some of the aerosol particles over time. And of course, when we have different wind conditions or temperature conditions, we can also have something like this. But now when we use the air purifier, we can see that we can beat easily the window ventilation in this case. Of course, here the temperature difference between inside and outside wasn't that large. But you have to take into account when you are frequently opening your windows, then the temperature difference between inside and outside will decay. And after a while, you are ending up with a situation like this, meaning that the window ventilation doesn't work very well anymore. Your air purifier, on the other hand, works always in the same manner, no matter how large your windows are, no matter how the temperature difference is, no matter how strong the wind is blowing outside. So here you always have the same decay rate. And now the interesting feature I would like to point out here is that if you consider a room where you have no people inside, no barriers, but tables and chairs, you have the green decay rate. You see the green here. Now we put people in the room, like in a classroom, but we don't have the transparent barriers. We have the red one. And now we add the barriers as well. And we see we have the blue one. So the conclusion is, no matter what you put in the room, you will always get a very, very similar decay rate. The decay rate is actually independent of what you are putting into your room. And that's why you know, you don't have to worry about the protection barriers or movement of people and so on. The air purifiers will always do their job. They will always keep the aerosol particles on a very low level if you let them run all the time. So we have outlined that in a couple of studies. You can study that in more detail. So now what the people are usually recommending is that they are not saying, please use the air purifiers. They say, please use the window, that's good enough. And don't open the window too much because then it's getting cold and windy in the room. So only do that for 3 minutes. So what does it mean? Okay, now we start here. We open the window for 3 minutes. It means that the decay of the aerosol particles goes to this location here or to this one, depending on this trajectory you are. But let's consider we are going to this position here after 3 minutes. Then we close the window, and this means the aerosol particle concentration stays on this level. So you see, that's the problem of the, let's say, shock ventilation. You do it for a short time, you're rejecting some of your aerosol particles, usually not many, and then you close the windows and you go until the end of the hour on a high, in a room with a high virus load. So that's a problem. And here, these devices are working all the time. That's a continuous rejection of the aerosol particles and not an intermittent one. And that's why these devices are working so much better. Let me finally outline you a bit more the problem of the window ventilation. So here we consider, let's say 45 minutes, so a typical class hour. And here we have the virus load, the number of viruses per cubic meter. So if you're, let's say, getting into the room, and let's say 1 or 2 or more people are infected, then of course we have production of aerosol particles in the room. So that's our source term here. And of course the virus load in the room depends on the strength of the source and depends on the time. That's of course why it's raising here. But we have here another factor, and that's the room size. So the larger the room, the lower the virus load will be. So that's why outside, the room is extremely large, so we don't have to worry about the indirect infection. If you are in a church or a big town hall, the room volume is quite large, so we don't have to worry about the indirect infection. But in a classroom, that's already quite problematic because we stay there for a long time. If we go into a much smaller room, let's say a taxi or a car, then of course the room is extremely small. And then it's extremely dangerous. So we have to go to a much more, let's say, air exchange rates than in a classroom. So in a classroom, we say 6 to 8. In a taxi, we would say 50. And maybe even more than this. So this is something you always have to take into account. Your room size matters quite a lot. So now, of course, we can consider now the integral here. So more the medium virus load over the hour, and we consider this at 100%. So that's the dashed line over here. So now we do the shock ventilation over here. Now what's happening? Well, if you have the shock ventilation, then of course at the beginning the virus contamination raises. Now let's consider that we are able to reject all the viruses over the 3 to 5 minutes, and then it raises again. So it means that we have on average a virus load of 50%. So when you have a perfect rejection of the aerosol particles within this shock ventilation time, you can reduce the virus load by 50%. Not more, that's the maximum. So now in practice, of course, we saw that before, you will not be able to reject all the aerosol particles or the viruses on the room. So you will probably have the raise at the beginning, and then it goes down to this point, and then it raises again. So the medium will be something like this here. So you will stay at the end somewhere between 100% and 50%, no matter what you're doing. So that's the problem of the window ventilation. And of course, because it's getting windy in the room, because it's getting cold in the room, and because after some time it's not working anymore, because the temperature difference is getting too small, and it's too much work for the kids to do that. It interrupts the class. They will not do that. and then it's getting even worse over time. So that's the main problem. So now let's consider the air purifier. In this case, of course, we also have a increase at the beginning, but then it stays on a constant level. And where this level is, this depends on the volume, let's say, of the filter. So basically, and the exchange rate. So that's the issue. So if you raise the case, the number of air exchanges per hour, you can reduce the virus load to even lower level. So that's the point. You have a continuous rejection of the aerosol particles, and this causes a constant level of the virus load in the room, and the level of the contamination is given by the size of the room and the air exchange rate. That's why this is so important. And of course, this clearly demonstrates the benefit of the technical ventilation systems in contrast to the mechanical ones based on window ventilation. So let me come to my conclusions now. So at the beginning, I showed you that surgical masks and mouth and nose coverings are pretty good because in face-to-face conversations, they limit the spread of the virus over the distance, and that's why they protect others from the direct infection. But because of the leakage flow, they don't have any self-protection capabilities. If you go for the N95 mask or KN95 or FFP2 in Europe, then you have a very good protection against the direct infection and against the indirect infection. And this gives you a very good self-protection, but also a good protection of others, because if you're self-infected, you're not, let's say, bringing the aerosol particles into the room. So all the other people are safe if you are wearing this mask and you are infected. If you use protection walls, then of course you can also, let's say, become more or less safe from a direct infection when you are sitting very close to each other and without a mask. So this is very good for a classroom, for an office, but also for shops and so on. And with the perimeter edge I've shown before, this is also much better compared to the ones you typically see on the market. And of course, because you cannot wear this mask all the time, this is one important, let's say, safety measure, but it is only helpful against direct infection. It cannot give you any protection against the indirect infection. That's why you need room air cleaners on top of that. So you need to use these two safety measures in combination to get a, let's say, rid of the direct infection risk and to minimize the indirect infection risk. Here you only need the mask to get protection from both of these transmission routes. But here you need both. But of course, the good point is you don't need a mask anymore. And that's why we are recommending in schools and offices let's say, these protection measures. And we have strong, let's say, funding programs now in Germany over, let's say, I don't know, about €1 billion already to install these kind of devices in classrooms. So it was quite a success, this research over the past 1.5 years. And if you are interested in further details, we have a number of articles and videos and so on. So if you're interested, you're welcome to have a closer look. With this, I would like to thank you for your attention, and I'm looking forward to your questions. Thank you very much.
Thank you very much, Professor Kähler. So now it is the time for questions. Questions from the audience. Please ask your questions, unmute yourself and ask questions, or you can type your questions at the chat so that we can ask the speaker.
I can start. This is Kim Prather. I'm at UC San Diego, and I really enjoyed your seminar. And I've spent the last year and a half thinking about aerosols and transmission of SARS-CoV-2, just like you have. And I learned a lot from this seminar. And I just have a couple of questions. I mean, I've been lately really pushing, I would say, the importance of having HEPA filters distributed through a classroom. I've been helping schools reopen, and I think that's really like an important safety net. And so let's turn this on. So, you know, I guess what I'm trying to think about is you said some things that sort of didn't, how do I say, I've done measurements around spatial aerosols are super patchy, right? And so I just want to understand two things. One, you said that, you know, basically it doesn't matter where you put the HEPA. That doesn't quite jive with if you had a super emitter at one point in the classroom. You're talking about it's already distributed. So how do you address that? But more importantly, like for me to understand your measurements, what is the lowest size range? Because different particle sizes will behave very differently. And I measure all sizes down to, you know, 100 nanometers. So they show huge variations across the room. So can you comment on that, please?
Yeah, so we also use particles going down to 100 nanometers. And let's say we have a particle size range in the between 100 nanometer and 2 micrometers, because this is usually the typical, let's say, diameter of the aerosol particles you are emitting, and which stay over longer time in the room. So these are the most critical ones, and these are also the most critical ones because they are most difficult to reject by filter ring, by HEPA filter, but also other filters. So that's one problem, because some groups are using quite large particles and poor filters, and then they say poor filters are good enough, and that's because they use large particles. So I can always recommend to do it as you did with the small ones, because then you have really the worst case scenario. And that the point is, the particles, the aerosol particles, no matter if they are 100 nanometers, 2 micrometers, or 10 micrometers, they are always distributed with a flow. So it's a flow physics problem at the end. And that's why the turbulence level in the room matters quite a lot.
It matters a lot.
Matters a lot. The turbulence level is really important. So the people sometimes say, you know, you shouldn't move in the wall, in the room, you shouldn't breathe, and so on. But that's important. The more you move, the more you breathe, the more you shake with your hands. That's always good, because it enhances the turbulence level in the room and it enhances the mixing. And this has basically two important aspects. The first one is, of course, you enhance the mixing. So that's always good. And because you are, in this case, lowering the virus load. Because what the people usually think is you have the device at some corner and you are emitting the particles at the other corner, and the particles are always moving the same trajectory. And then when the person is sitting close to this trajectory, it can be infected. But that's the wrong thinking. You have a turbulent flow, so the particles will never go the same trajectory to that location. So if you have a large turbulence level, you have always quite close to the mouse a big spread of the particle cloud, which lowers the particle concentration. And when you have now a turbulence level in the full room, the trajectory will be always a different one. And that's why it's very, let's say, very safe using this devices. So you don't have to worry about that the particles are going through the room to the air purifier. That lowers the virus load locally. And that's one big protection. And of course, when you consider this with an HVAC system or with window ventilation, that's actually the same. So you profit from the turbulence level, and that's why the turbulence matters so much. And the particle size, what you say, that's not so much of an issue because the flow is the driving force. It's not the kinetics of the, let's say, the particles itself. No?
Okay, no, you taught me a lot. I guess I was thinking about the point source, and that, you know, and that if you had someone really close to someone, unless they were both wearing masks, which we hope they are, that it's a problem. I still think that, like, again, I would love to talk with you more about this. This is fantastic. It's a different twist. The turbulence, I want to understand what controls that, but thank you. I don't want to take up all the time. I could, but I won't.
Yeah, but what you're thinking is fully correct. But that's what is close to an infected person, that's a direct infection.
Right, exactly.
There you need another thinking. There you need the protection wall, the mask, or the distance.
Yep.
But once the direct infection risk is minimized because of the protection, the indirect infection you have to consider, and there the turbulence level. Matters.
The turbulence matters, right? I get that, but it's the up close that I'm worried about in classrooms right now. But thank you very much. It was a great seminar.
Thank you.
Thank you very much, Professor Prather, for the questions. So we have another question from the audience from Ken Arnold asking, has the impact of the temperature or humidity on the aerosols been evaluated in these studies?
Yeah, this is still an open question, I would say. Of course, we know quite well what humidity and temperature matters to the size of the aerosol particles. Actually, at normal room conditions, when you have, let's say, emitted some aerosol particles, normally the liquid phase will evaporate more or less immediately. And then you have the aerosol nucleus going through the ground, actually the dried salt with the virus and so on. If you have a high level of humidity, then of course it may be that the aerosol particles keep a little bit of their liquid phase. And it can be also that the aerosol particles raise a little bit in size. But you should always keep in mind that even when we have a very high level of humidity in the room, the aerosol particles will stay aerosol particles. They will not become droplets and fall down within, let's say, a significant time of the people stay in the room. So if you are considering making them big, that they fall down and use this as a kind of safety measure, this will not work. If, let's say, an aerosol particle is emitted and it has a size of 1 micrometer, you will not bring it to 10 micrometer with the humidity. And if you do, it doesn't matter, it will stay as an aerosol particle, even when it's 100 micrometer. So that's why I think in terms of fluid mechanics, this doesn't matter so much. There's another aspect, of course, namely, let's say, the lifetime of the virus, depending on the humidity in the room. And here we can say, let's say, if we consider something like a class hour, 45 minutes or an hour, it's not so significant, this consideration, because most of the virus will be infectious over this time. I mean, we know from other studies that the lifetime of the virus is about 1.1 to 1.2 hours. But let's say over the period of time of an hour, we can consider them as infectious. So it doesn't really matter if they are infectious for an hour or 2 hours if you use an air purifier, because they are gone after 3 to 6 minutes. That's let's say more or less the lifetime of the virus in the room when you have an air purifier. So after 3 to 6 minutes, most of them are 50% are gone. And that's why here it helps also quite a lot. So that's why I think even if there are some unanswered questions regarding humidity in the moment, I think when you use this kind of safety concept, you don't have to worry about that so much. Hope that answered your question, at least partly.
Yes, thank you. So the reason I asked the question is because the most common mechanism is heating, ventilating, air conditioning that essentially is typically, like in our environment, is taking relatively more humid from rooms being put into the HVAC system, mixed with air from other rooms, and then exhausted into other rooms. And so my concern was, is the reduction in humidity that happens for perhaps when the air gets chilled and condensate comes out of the air, if that is likely to make it better or worse. And since there's more mixing, and since the virus particles last for a long time, it's a little bit different when you've got an HVAC system that's mixing multiple rooms in the same building, for instance.
You are absolutely right. And of course, I cannot recommend using HVAC system working in this way. Either you are operating then with H14 filters, then it doesn't matter so much, because if the air passes this filter before getting into the next room, that's fine. But if you don't do that, you shouldn't use your HVAC system at all. So what in Germany, for instance, the regulation in the moment is to go for 100% outside air if you use a HVAC system, and no recirculation. No, so that's a waste of energy, of course, I know, even in the winter time, but that's it, what they do at the moment.
Okay.
It's still better than opening the windows.
Yes, thank you for that. And excellent presentation. Thank you very much.
Thank you very much.
Thank you, Professor Kähler. I'm wondering, do you have the link that you showed before on the YouTube that's showing when people sing and or playing the music instrument, they also they have the pattern of releasing the aerosols. So do you have the link prepared here or no?
Oh, with my music research, you mean?
Yes, yeah.
Oh yeah, if you are interested in all my YouTube videos, we have already we have a let's say a YouTube page. Just type in YouTube LRT7, no space in between, LRT7, and then you will get to my my YouTube page with all the videos. If you're interested in the reports, just go type in on Google Uni BW, so my university, LRT7, that's my institute name. And then you find there the button with the English version of my homepage with all the articles. Also, most of the articles are on the midwife medical server, if you are interested as well. So if you don't find them, just send me a link. An email, and I will provide you with all the links.
Thank you so much, Professor Kähler. Thank you for the wonderful, enlightening seminar. We really appreciate it. And then as a token of appreciation, we would like to present you a small gift. Okay, so although you didn't show up, cannot come to America for delivering this seminar on campus, but we'd like to send you the small gift to you. So can you allow me to share my screen so that
sure.
Yeah, so I like to share my screen here. That is here, and then the gift I'm talking about is here. Okay, so let me bring to this gift. Yeah, this is the
wonderful.
So we'd like to send that to you, to Munich. Hopefully it is before the Oktoberfest, so you may still can be able to use it, get to that festival. Yes. So,
excellent. Thank you very much. It was a great pleasure talking to all of you. And thank you very much for your questions. And it's, of course, it would be better to visit you directly as 2 years ago, but hopefully maybe next year or in 2 years, we will have the chance to meet you other again at your place, or please come to Munich.
Yeah, thank you so much. Thank you. So thank you everybody for attending this seminar. Thank you, Professor Kähler, again for spending your time in your weekend time to delivering this wonderful lecture. So thank you very much. So by that, so we can close our seminar today. So thank you.
Thank you very much. Have a nice weekend. Bye-bye.
Yeah, bye-bye. Have a nice weekend.